All right, folks. Today we're going to give a simple talk on IQ data. IQ data is heavily used in all your software-defined radios out there, any kind of digital communications, radar, sonar, radio astronomy. All of that is going to have some kind of IQ data that you need to process. So let's get into let's just say a motivation for it or why we would want an IQ demodulator. So let's take our example here. We have a local oscillator at 180 megahertz. We have an incoming signal at 181. This is going through a mixer. For our purposes, let's just say it's a ideal multiplier such that the product's only going to be the sum and difference of these two guys. We low pass filter it so that we only are picking off the difference frequency. And it's clear that this A to D analog to digital converter running at a 10 meg clock will only see a 1 megahertz sine wave, right? Because the difference between 181 and 180 is 1 megahertz. So far, so good. But now, let's say the input signal is 179. Well, the analog digital converter over here will also see 1 megahertz. Some might say it's a -1, but the analog digital converter will not be able to tell that because it only has one A to D. It has nothing to reference to it or compare it. So in terms of at the A to D here, we cannot tell whether basically 179 is the input frequency or 181. And so basically with this current design, as I said, we cannot tell whether the signal coming in was 181 or 179. So how can we solve this? Answer is to implement a IQ demodulator. And this is the high level here. The RF comes in, it gets split, essentially goes to two mixers, and the local oscillator is generating a cosine signal and a sine signal. All right, so now let's go through our example. 181 comes in. Again, the LO down here is set to 180 megahertz. So the I port will have the cosine of 1 megahertz. The Q port, we will have the sine of 1 megahertz. All right, so far so good. Now 179 comes in. The I port will be the cosine of 1 megahertz. The Q port will be the negative sine. So I think it's clear now that now we have an ability to determine whether the input frequency is either above or below the LO. And here's the math for this, right? So if 181 is the input frequency, the LO is 180. Again, the I is the cosine, the Q is the sine. This is how down here you express it mathematically, and typically it's expressed in this compact form. So this is a positive e to the j 2 pi 1 megahertz times time. For the 179 case, it's an e to the negative j 2 pi 1 megahertz times time to indicate that it's going to be a negative 1 megahertz frequency in that it's 1 megahertz below the oscillator. Okay, that's what we mean by negative frequencies. It now lets us know it's 1 megahertz below the oscillator frequency. And we can do that because we have essentially an I and Q to compare it to. So this is not just some magical thing. Many spectrum analyzers have IQ analyzer pages here that let us see the actual I and Q signals. And here is one for the Rode spectrum analyzer. Here is the I trace. The bottom is the Q trace. So again, this is just showing you guys this is not just some mathematical white paper, that this really is real signals that we can look at with modern equipment. So this would be a typical example of a modern receiver. The RF comes in, it's somewhat bandpass filtered, amplified. There's an local oscillator that mixes it down to some center IF frequency, and then that IF frequency is digitized and converted to what is essentially called baseband IQ. And this is the I and Q data that would go down to get further processed. So we've talked about IQ demodulators, but we can also do the same thing for transmit. Obviously, that would be called an IQ modulator. It's the same idea, it's basically in reverse. You have the LO, which is the center frequency of where you want to transmit, and you feed this thing an I and Q signals to create the final RF signal. So this I and Q are baseband signals, and the LO here is what's basically being the carrier of the final frequency we want to come out. So let's just go right into an example. So let's just say we want to create a signal at 180 megahertz, and we want to apply 10 dB of attenuation and give 45-degree phase shift. Here's the equation of how we do that, and here's explicitly how we break out the I and Q numbers. So chug those in your calculator, and that's the I and Q numbers that if you presented to a IQ modulator, it would attenuate the signal by 10 and put a 45-degree phase shift. So this is one way how you can start representing digital bits. Basically, every bit will have a unique phase and attenuation. They call it a fancy name like QAM64, but it's basically using this equation. You're representing all your possible bit patterns by discrete amplitude and phase values. So here is just showing how we apply the I and Q into the modulator, and if we look at the output of the IQ modulator, we will see a signal that is 10 dB attenuated and a 45-degree phase shift is applied. So it's no accident this is a standard architecture for any kind of digital modes, in that to represent the different binary bits, you're simply picking different attenuation and phase, and they get represented into this I and Q picture here. So an IQ modulator or demodulator essentially preserves the amplitude and phase of a signal. And when you do that, you can create any type of modulation signal. So that is why IQ modulators are very common, because if the modulation scheme were to change, the hardware does not.